Welcome to the WISP lecture series. We are very happy to have you here. Henry, you work in cryptography and build systems to protect users using cryptography. And so it's morning in Massachusetts now, where you're located at MIT. We are all very happy to have you here for this talk on safety pin. So please. Stage is yours.
Yeah, thanks so much for the invitation. So I was saying earlier, I'm really sorry to not be able to be there in person, and I'm hoping that some point in the future I'll be able to come and meet you all. So this is joint work with Emma Dotterman, who's a fantastic PhD student at UC Berkeley and did most of the heavy lifting on this project, and David Mazieres, who's a professor at Stanford. And this is kind of a systems-oriented talk because it's a systems-oriented paper, but there's some cryptographic ideas in here. So I hope that this will appeal to both sides of the audience here. So the problem that we're addressing in this work is the following. You have a phone, whether it's an iPhone or a Google phone, and you want to back up your data to Google servers without Google getting access to your backed up data, your photos, your notes, and everything else. So you should think of kind of the threat we're defending against is an intelligence agency or police agency in whatever unfriendly country of your choice goes to Google's data center and is trying to extract your sensitive data from whatever's in the data center. So since many of you probably haven't seen this before, I'll explain briefly first how these mobile device backups work today. And this is kind of a cartoon simplification, but captures the key ideas. And similar ideas are actually used in iOS for Apple phones, Android phones, and also in something called Signal secure value recovery, which is Signal's backup feature. And I should say also, please feel free. It's a little hard to interrupt someone on Zoom, but please feel free to jump in. Maybe I can see if you raise your hand, or just unmute yourself and yell at me if you want to ask a question in the middle. I think it's. So yeah, I'll trust people to do that. So the way this works with these encrypted backups today is that Google has a bunch of storage servers in its data center, and they also have a hardware security module that I'll call an HSM. And a hardware security module is just a kind of a really slow, physically protected computer. So think of a small microprocessor coated in epoxy in a hardened case that has a secret key in its memory. So that's a hardware security module. So when you back up your Android phone, your phone creates two ciphertexts. The first thing it creates is it samples an AES key, so a symmetric encryption key, and it uses that encryption key to encrypt all of the user data, the photos, the notes, everything else. And so that's kind of a big ciphertext. And then it encrypts this AES key alongside your PIN, the PIN that you use to unlock your phone, with the public key of the hardware security module. So this is kind of a small ciphertext because it's just encrypting a PIN and this AES key. And your phone sends both of these things to Google's data center. Oh, it looks like this image got messed up. Sorry about that. So then when you drop your phone in the lake, you get a new phone and you want to recover. What you do is your phone sends an encryption of your PIN, the PIN that you use during backup, with the public under the public key of the HSM to the data center. And Google gives both of these ciphertexts to the hardware device. So the first ciphertext contains the encryption of your true PIN and the encryption of this key that is needed to use to decrypt your backup. The second ciphertext contains the encryption of the PIN that you're using during recovery. And what the hardware device does is two things. First, it checks that the pins on these ciphertexts match so that you're recovering your ciphertext with the same PIN that you used during backup. Essentially that you're the right person, you knew the right PIN. And the second thing it does is it checks that you haven't guessed the PIN too many times. So there's some rate limiting. So for example, you can guess 10 pins a month, and then Google will lock your account, or the hardware security module will lock your account and prevent you from doing any more PIN guesses. So both of these checks pass. The hardware security module will decrypt this AES key that you need, and you can download this big ciphertext, download this key from the HSM and recover all of your data. So does someone want to ask a question about this? I went through this quickly, so I just want to make sure it's clear before I go on what the role of this HSM is.
I would have a question.
Yeah.
If the attacker, like the attacking model, is a nation state or whatever, because I actually was wondering when I installed Signal a few weeks ago that they only want a 4-digit PIN, right? And I mean, of course, for the CIA or for the NSA or for whoever, like guessing 10,000 keys is not a big problem. So are these like, is this PIN is only useful for protecting against like somebody trying to steal my data by claiming that I have lost my account, right? Or are there other measures in place to prevent like offline attacks against this? Like if the NSA walks to the server farm and like just takes out the hardware module or whatever.
Yeah, so the only thing that protects you against offline attacks is this hardware module. So if you're worried about someone breaking into the hardware module, say a nation state comes to Google, takes away their hardware module, takes away the data that's in their storage servers, yeah, then you have a problem. So this is essentially
right?
What's that?
For this, like a 4-digit PIN wouldn't suffice, right? But you could have a longer PIN, and then you would.
Exactly. You can use a longer PIN. It turns out that nobody does. So this is kind of why, this is why they use these hardware security modules. But this is an excellent question. And this is kind of, I guess, exactly what I wanted to talk about next. So why these systems are useful is, first, it protects you against the compromise of Google servers. So an attacker who comes in and compromises all the servers, compromises the data center network, still doesn't get more guesses at the PIN than a normal user would. They only get 10 guesses at the PIN, provided that this hardware security module is doing its job, keeping its secrets. The other major benefit is it's super convenient for everyday phone users. You just have to remember a PIN. The user experience doesn't change. You don't have to store some 256-bit key somewhere that you might lose. So this is why everybody likes this strategy. Of course, the problem now is that the security of this entire system now rests on the security of this hardware security device. So an attacker who can get into the data center and extract this secret key from this hardware security module now can decrypt everybody's backup, right? They can brute force guess these 4-digit or 6-digit pins, and they can get everyone's data back. So this is like a single point of security failure. And the reason why we should worry about this is that it turns out these hardware security modules, with enough effort, you can actually extract the keys from them. So there's many, many examples of this. I just picked one from last month, which is a group in France extracted the secret key from a Google Titan hardware device. It's not that easy to do. So they had to use what was it? Some kind of acid to burn off, the layers of epoxy around the chip. I mean, I think it's not easy, but it's possible. So this is why we worry about the compromise of these hardware security modules. So the system called SafetyPin we've built is trying essentially to do two things. We're trying to get the convenience and the scalability of these pin-based backup systems that people are using today, but with much, much stronger protection against compromise of hardware modules that constitute the system. So let me explain in a little bit more detail what I mean. So today, there's kind of one hardware module in the data center and a bunch of storage servers. And we'd like to move to a world in which there's thousands of these hardware devices in a data center and the same amount of storage. And the security that the property that we want essentially is that so I guess today, if an attacker compromises one HSM, they get everybody's data. We would like to be in a world in which an attacker has to compromise a large fraction of the hardware devices in the data center before they get anyone's data. So think of there being 10,000 hardware devices in the data center, and the attacker has to compromise 1,000 of them before they can get any user's backed up data. So it's still possible. It's still possible for an attacker to go in and compromise 1,000 of these modules, but it's going to be much more expensive. The other property of the system that's important is we don't want to kill the performance. So today, your phone just has to talk to one hardware device during this recovery process. And we'd like to kind of maintain this in the new system, where we'd like that your phone only has to talk to, say, a small handful of these hardware devices. During recovery, the phone shouldn't have to talk to every one of these thousands of devices. Otherwise, the performance would just be horrible. So let me pause here. Is there another question about the setup before I go on?
One short question about what exactly do you mean by HSM? Because it can mean a lot of things. Do you mean the big Gemalto SafeNet $10,000 things, or do you mean the small UB HSM $200 things?
Good question. So which hardware am I referring to exactly? And I'm going to kind of, so I'll say, I guess in the context of a data center, I'm referring to the $10,000 things, kind of the industry grade ones. For our experiments, we're going to use the $50 things because we couldn't afford, 100 of these $10,000 HSMs. But it really doesn't matter too much. The techniques are going to be the same for both of these devices, mostly because the hardware is almost exactly the same on both of these devices. As far as I can tell, the only thing that separates the $10,000 SafeNet HSMs from the $50 USB key HSMs is the physical protections one and the marketing is the second. So unless this is my understanding. So I hope, did that answer your question?
Yes, thank you.
Good.
Speed would be a third thing that definitely separates.
Yeah, the speed difference. So it's not as big as I would have thought, but yeah, there is some performance difference between these big industry grade HSMs and these tiny YubiKey things. Yeah, great question. Anything else? Okay, I'll keep going, but again, please feel free to stop me. So the kind of premise here is that if we have more HSMs, we increase the number of these hardware modules in the data center, we'd like two things to happen. We'd like better security and we'd like better performance. So kind of today, if Google adds more HSMs to their data center, the security situation doesn't change at all because you only have to compromise one to get at user data. And with this system, the idea is you have to compromise more and more and more HSMs as the number of HSMs in the data centers increase. At the same time, we kind of like performance to scale with the number of HSMs. So today, if you double the number of HSMs, the throughput doubles. And we'd kind of like something similar to happen with this new system. And just to kind of drive home the point that I'm trying to make, the thesis of this work, kind of the premise that underlies this work is that compromising more hardware devices is going to be more expensive. In particular, these physical attacks, the cost of the physical attacks are going to scale linearly with the number of HSMs that an attacker has to compromise. In addition, the attack gets much noisier. So, breaking into a data center and hauling off 1,000 HSMs is going to be much louder than just taking one. Oh, good. There's a question in the chat. So yes, the industry grade HSMs are just encryption decryption oracles. You don't store any user data in HSMs. And the reason for that is the HSMs have basically no storage. Even the fancy ones have like a megabyte or so of storage. So you have to store the data elsewhere. Good. So, okay. And then the third reason why I think this is interesting is you could use a diversity of HSM types, models, manufacturers to get some protection against software bugs too. Okay, so that's kind of the setup. This is what we're trying to do. I'm now going to sketch kind of the overall design of the system, and then I'll talk about two technical challenges that come up that we had to address to make this work. And then at the end, I'll talk about the experimental evaluation that we did to try to get a sense of how realistic this type of system would be in practice. Any other questions before I jump in? It's very difficult when you can't see people's faces to judge, judge. But I'll keep going and then stop me if please again stop for questions if something gets confusing.
We have one question in the chat. What happens when an HSM breaks?
Yeah. So fault tolerance is super important. So I'll come back to that in maybe 2 or 3 slides. But yeah, this is something that you worry about. Cool. Okay, so let me try to sketch. This is not obviously a formal statement of the security property that we want. Check the paper if you're interested in that. But essentially what we'd like to say is that an attacker's, the advantage an attacker has in recovering an honest client's data is not much better than just the chance that the attacker can recover your data by guessing your PIN. And this should hold even if the attacker controls the data center, controls the storage servers, and can adaptively compromise some fraction of the HSMs after the client backs up its data. So this adaptive compromise is what makes the security non-trivial to achieve and is kind of the source of many of the headaches. So the idea is you give your ciphertext to Google, and then the attacker comes to the data center and looks at your ciphertext and decides which HSMs to compromise based on all of the information it sees. And additionally, we'd like this sort of security property to hold even if an attacker compromises all the HSMs in the data center after your recovery is complete. So I guess the details are not super important. I guess what is important is that we're trying to aim for a pretty strong notion of security here, much stronger than you can get today. So let me explain at a high level how this system works. And it's actually pretty straightforward. It's not exactly maybe the first thing you would think of, but this is not far off from that. So I'll explain how backup works and then how recovery works. So the setting is we have all these HSMs, and each HSM has a secret key stored in its brain, and it has a public key that everyone knows. And the phone, when you go to backup, has your screen lock PIN. It has your secret data, so your photos, your notes, and all that stuff. And the phone also has the public keys of all the HSMs. The way the backup process works is as follows. So what you do is your phone samples a random AES key, so a random encryption key, and it splits this key into some number of shares using an additive secret sharing scheme. So think of this, the number of shares is something like 40, where this 40 depends on the security parameter. So these are just additive shares of the secret key. So these K1 up to K40 add up to this AES encryption key that you picked. Then what the phone does is it samples a set of roughly 40 HSMs by hashing the username of, let's say, the Google username of the phone's user, along with the screen lock PIN. So you just hash the user ID, you hash the PIN, and this gives you the identities of 40 HSMs. And the last thing you do is the phone outputs an AES encryption of your data, so your photos, your notes, and all that stuff, under this encryption key that you've picked. And then it encrypts each share of this AES key with the public key of the corresponding HSM. So you pick 40 HSMs based on the PIN, and you give each HSM a share of this encryption key. And this is the ciphertext that you output. So this first part is kind of the bulk encryption of your data. The second part are just encryptions of the key shares to one of each of the HSMs. So it turns out the public key encryption scheme that you need to use here has to have some extra properties that I'm not going to talk about. It needs to be key private. It needs to be secure under selective opening attacks and more. But this is kind of a cryptographic detail that I'm not going to get into. But is there any question on what's going on here? Of what the intuition is? So, okay, let me show it in picture form, or let me give some more intuition about why this is the right thing to do, and then maybe more questions will come. So essentially what happens here is that there are 40 HSMs an attacker could compromise to get your data. You know, these HSM I1, I2, I3 up to I40, if the attacker compromises those HSMs, it can decrypt these ciphertexts, it can then decrypt your data. So there's 40 HSMs that an attacker has to compromise to get your data. This is a relatively small number of HSMs out of the, I don't know, tens of thousands of HSMs in the data center. But the problem is the attacker doesn't know which 40 it needs to compromise. And the reason is because the 40 HSMs that you picked depend on your PIN. So the attacker's best strategy essentially is to just guess your PIN at this point. So because the attacker doesn't know which PIN you used, it doesn't know which HSM to compromise, and it's kind of stuck. The best thing it can do is guess your PIN, and it has whatever, a 1 in 10,000 chance of guessing right. And if the attacker guesses only, say, like 39 out of the 40 HSMs that you used, it doesn't have enough information to decrypt your ciphertext. So the attacker really has to get all 40 before it gets anything. So this is kind of the intuition. This is obviously not a proof, but we have some formalism and proof in the paper if you're interested.
One short question.
Yep.
The secret sharing scheme that you're using, that's not an M of N scheme, but you actually need all the 40 key shares to reconstruct the key, correct?
I'll come back to this in 1 second, because for fault tolerance, I simplified a bit, but yeah, you can use an M of N scheme for fault tolerance too. Good. I'll come back to that in one second. So I'll just say how recovery works. So it's kind of works in a straightforward way. What the client does when you come online with your new phone, you ask for these ciphertexts, and then using your screen lock pin, the phone computes the set of 40 HSMs it needs for recovery. It then sends these key share ciphertexts to the 40 HSMs, which perform the decryption, which let you recover your backed up data. So this is I guess the key property here is you only need to talk to 40 of these HSMs instead of all of the 10,000 HSMs in the data center. So yeah, I guess the one thing you might notice is that actually when you do this recovery, the 40 HSMs that you talk to leak information about your PIN. And that's because which 40 HSMs you talk to depends on your PIN. So the attacker sees which HSMs you talk to, there's some leakage of your PIN to the person who's running the data center. So with this system, every time you recover your backup, you need to change your PIN. This is just a limitation of the way it works. But okay, let me talk about fault tolerance. So these HSMs don't last forever. Maybe they work for a year or two and then they fail. And of course, you want to recover your backup even if they do. So the way this works today is that each logical HSM is actually implemented with something like 5 or 10 hardware devices. So you can recover your data as long as not all of these hardware devices, these replicas, fail. And with SafetyPin, you can just replace this additive secret sharing, as Matthias mentioned, with Shamir secret sharing. So you split your key into something like 50 shares, such that any 40 of these shares allow you to recover the secret. And then good. A question, yeah. I think I answered the question in the chat. And say again?
Yes, the question is already answered. I wanted to interrupt you before, but you answered it on the slide, so it was perfect.
Good. Yeah. I'll try to be upfront with the limitations, of which there are, a few. So that's definitely a big one. So okay, so this allows you to recover if even some fraction of the HSMs fail. So okay, so that's kind of the basic design. There's a bunch of other things that come up when you actually think about how this would work in practice. So I'll talk about two. The first I want to talk about is after the fact compromise of HSMs. And again, this is not, I think if you sit with this design for a while, you would realize that this is actually a serious problem. So as we just discussed, when the client recovers, so it recovers its backup, the client reveals which 40 HSMs have the secrets that are needed to decrypt the client's data, right? There's only 40 HSMs that the attacker needs to compromise to recover the client's data. And during backup, the client reveals which ones these are. So a clever attacker can kind of watch me run this recovery process, and then go with the screwdriver to each of these 40 HSMs and pry out the secrets, and then get my data. So is this clear? Is this attack clear? This kind of watch me recover, see which HSMs I talk to, then run with the screwdriver into the data center and start pulling secrets out of this small number of HSMs.
One question.
Yep.
So if the attacker knows which 40 or which N HSMs are used, does he also know in which order like they constitute my key in a way? Because like if the number would be high, like I mean, you would have 40 factorial different keys, right? I mean, this would also be some layer of security.
Yeah, yeah. I think the fact that the pin space, there's so few pins, mean that this doesn't buy you much, right? Because yeah, I think this is the issue. Yeah, so the question is, what about adding a bunch of noise? I think the issue with adding noise is, again, the number of pins is so small that essentially the attacker can kind of subtract off the noise without too much work. Maybe there's a more clever way to do this that we didn't think about, but I think, yeah. So, okay, so what we do instead, you can think of this, maybe this is kind of a hack, but it seems to work well enough, which is that after recovery, each HSM that was involved revokes its ability to decrypt the client's ciphertext. And by revokes, I mean the attacker, the HSM can no longer decrypt that ciphertext, even if the attacker gets in its brain and extracts all of its secrets. So the primitive that's used here is something called Punctuable Encryption, which is a relatively recent cryptographic primitive, but is actually not that hard to construct. So the way this works, these punctuable encryption schemes work, and there's a number of them in the literature. At a very, very high level, the secret key that the HSM holds now consists of a big array of secret keys. So for us, this ends up being something like 64 megabytes of data. And there's kind of a corresponding public key for each of these secret keys. And when the client encrypts, it encrypts to some subset of these public keys. And to revoke its ability to decrypt a certain ciphertext, the HSM just needs to delete some of these secret keys. So the secret key is a big array, and to revoke your ability to decrypt, the HSM punctures this array or deletes the elements of this array at certain places. So this is at a very high level what punctuable encryption schemes do. So that's fine. The problem is these HSMs, as I mentioned before, have almost no storage, right? They have maybe a megabyte of storage you can play with. And this secret key can be 64 megabytes, 100 megabytes, depending on how you set the parameters. So what we do here instead is we have the HSM outsource the storage of this array to the data center while protecting the data against the data center and also protecting against future compromise. So I suspect that today's actual backup systems do some kind of outsourcing to the data center for storing these guest counters. But since these are closed source systems, I have no idea how they work. And I think they probably don't need this kind of puncturing property that we get. So I think this is probably new to them. So I guess before I explain it, is the kind of high level idea here clear? Sort of. Does someone want to ask a question? If something's unclear. Okay, I'll take that as everybody understands it perfectly, but I'm not sure. Okay, maybe something will come up as we keep going. Okay, so again, what we're trying to do is we have this big array on the HSM that we'd like to outsource to the data center in such a way that the HSM can still kind of delete elements of this array without, and protect kind of against future compromise. So the way we do this is we have the HSM first encrypt this array and then give the ciphertext to the data center. But we have to do it kind of cleverly to make sure that we can make kind of reads and writes and updates to this array efficiently. So what the HSM does is it gives this entire secret key array to the data center, except that it pairs up each of the elements of this array, and it encrypts each pair under a new secret key. So each of these elements of this big array are paired up and encrypted under a new secret key. So now we have a smaller array. And we outsource this smaller array as well. So we pair up and encrypt these elements. And so we have an array that consists of only one element, and that's stored in the HSM's internal memory. So instead of having to store, 100 megabytes of stuff, the HSM just stores one AES key. And then periodically, when this puncturing operation happens, the HSM needs to delete elements of this array. What it does is say it wants to delete this element. It deletes this element of the array, and then it re-encrypts each of these pairs on the path to the root under a fresh AES key. So it kind of replaces this key and re-encrypts this pair with a new key, which it then pairs up and re-encrypts. And eventually it gets to holds a new root key, and it deletes the old root key. So to just show this again, so if the HSM wants to delete an element of this array, it re-encrypts all of the pairs on the path to the root from that leaf to the root under fresh keys. And in doing so, deletes, sort of removes from this last pair the thing that it wanted to delete. So why do this? Well, the point is now if an attacker compromises the HSM, it can decrypt everything in this tree, but it still can't decrypt this deleted element because the key that's required to delete this, to recover this deleted element basically doesn't exist in the HSM's memory anymore. So this is kind of, even if the mechanics don't make sense, I think the high level idea you should remember is the HSM can outsource the storage of a big array while still being able to kind of securely delete things from this array. I guess the other property that's important for us is that this is relatively fast. So each read and write to this tree data structure only requires kind of logarithmically many operations in the size of this array that's outsourced. So this scheme for our key size, which is 64 megabytes, takes like half a second, even with these slow HSMs, versus if you were to read in and re-encrypt this entire array, which is kind of the naive way to do it, would take more than, I don't know, something like 40 minutes. So it's a huge speed up using this kind of tree data structure to outsource the storage of the secret key. Any questions about this? Cool. Okay, so I'll keep, well, I guess just to summarize what happens. So during recovery, the client reveals to the data center which HSMs the attacker would need to compromise to get its data. And the way we address this is by having HSMs revoke their ability to decrypt the client's data. So as soon as recovery completes, the HSMs delete these secret keys that they would have needed to get the client's data back. So that's the main trick. Okay, the next thing I want to talk about is how we do rate limiting in this big distributed system with thousands of HSMs. So just to remind you, the whole purpose of using these hardware devices is to limit the number of pin guesses that anyone can make on each user's account or on each user's backed up data, right? Because we want to prevent these offline brute force attacks against the pin. The problem in SafetyPin, the SafetyPin setting where we have tens of thousands of HSMs, is there's no single hardware device that has a global view of how many pin guesses a user made. Each HSM only sees the requests that come into itself. So we somehow need to reconcile these things, that the recovery is local. Each client only talks to a few HSMs, and yet the HSMs need to have some global view of how many pin guesses each user made. So our idea is to have the data center, again, outsource this work to the data center. So the data center maintains a log of each user's decryption requests. And the HSMs kind of enforce this rate limiting property on the log. So I'll explain in a little bit more detail how this works. But first, I just want to explain, drive home what the problem is. So why kind of each HSM keeping a local counter of how many guesses were made on a user's pin doesn't work. So this is kind of why distributed rate limiting is important. So here's all the HSMs. Imagine they each kept a local counter of how many guesses Joe had made at a pin, at the pin during decryption. So if Joe, so say now there's some attacker that's trying to mount a brute force attack against Joe's pin. What this attacker can do is it can basically hash, it hashes username and the guest PIN, it gets some HSMs, it asks some HSMs, these HSMs to do a decryption. These HSMs bump their guest counter for Joe's account. And then the attacker, say the attacker guesses wrong, it can't decrypt. So it tries the next PIN. And the attacker talks to some other set of HSMs, which each bump their guess counters. And then the attacker can make another guess and another guess. And you'll see that because each HSM only has a local view of these decryption requests, the attacker can make many, many, many more guesses than it should be able to against Joe's account, right? Than if we had some local global state that all the HSMs were kind of interacting with. So this is why rate limiting is important. We can't just have each HSM keep a local set of counters per user. So, okay, so what we do instead is we have a log, kind of a log that's stored on the data center. And each HSM holds the root of a Merkle tree computed over this log. So the log is kind of username and then the ciphertext that each user asks the HSMs to decrypt. And each HSM kind of in steady state holds a Merkle digest over this entire log data structure. So during recovery, what we require is the client to prove to the HSMs it's talking to that its decryption request appears in the log. So eventually the client has to log its decryption request first and then go to the HSMs and ask them to decrypt this thing. And the important property that we want, the invariant that we want this log to maintain is that each client should only be able to add a small number of records to the log, say every month. And if each client can only add a small number of records to this log every month, then this limits the number of PIN guesses that any user can get, right? Because to make a PIN guess, you need to add something to the log, and we're going to try to rate limit the rate at which this log can grow. So okay, so now this kind of works, except we need to figure out a way to maintain the log, even if the data center is corrupt. And essentially the way we do this is we have the HSMs check the work of the data center. So when the data center inserts a record into this log and gives the HSMs the root of the new Merkle tree computed over the new log, it has to prove to the HSMs that it didn't insert too many records for any user into the log. So I'm not going to go into the details of how this works, but you can do it with like a handful of Merkle proofs. And to kind of maintain scalability, so each HSM doesn't need to check every log insertion. Each HSM only checks, kind of randomly audits a fraction of these log insertions. And we choose this fraction to be large enough that many honest HSMs will check every insertion to the log and will be able to detect when something's gone wrong. So if the data center tries to cheat, many honest HSMs will catch it and the system will kind of come to a halt. This actually turns out to be super, super annoying to make work. So we have to use things like aggregate signatures to make sure that the bandwidth requirements for the HSMs is not too big. We have to do things carefully ordered with, there's a bunch of extra stuff that's described in the paper. But essentially after all this auditing stuff completes, each HSM now has a new digest for a new log and recoveries can continue. Okay, so that was very quickly two of the things that came up. So one was, punctuable encryption, implementing this on resource limited HSMs. The second is this logging for rate limiting. And I want to spend the last couple of minutes talking about the experimental evaluation here. So Emma, who is the PhD student doing all of the work here, bought 100 of these super low cost hardware security devices. So these are solo key HSMs. These are something like $20 or $30 each. And as someone mentioned, these are very slow. So just for reference, my laptop can do something like 15,000 ECDSA signature verifications a second. These solo keys can do something like 7. So they're really, really computationally limited devices. So she hooked these up to a Linux machine, which acts as kind of the data center. And then as a client, used a Google Pixel 4, so a modern smartphone. And implemented this entire kind of end-to-end system using these solo keys as kind of a representative slice of a bigger data center. So this is actually what it looks like. She got a bunch of powered USB hubs and hooked them all together to run the experiments over. So So cool. So the first thing is that even using these super slow solo keys, the end-to-end time, both for backup and recovery, is totally manageable. So both are less than a second. And this baseline scheme is our re-implementation of what Google and Apple do today. So it takes, this looks like a big jump, but at the same time, these times don't include the time it takes to even encrypt or decrypt your disk image, which is many gigabytes of data. So on top of everything else that's going on, this seems like a totally manageable cost. Yeah, the cost that's slightly more annoying is bandwidth cost associated with the system. So because of the fact that the set of HSMs in the data center is changing, and that these punctuable encryption schemes have kind of big public keys, each phone has to download like 2 megabytes of keying material for these HSMs every day. So that's annoying. The good thing,
why per day?
Because if you think about the HSMs, say you have 10,000 HSMs in your data center, and some number of them are failing, you end up having to rotate the keys relatively often. I guess even more specifically, this punctuable encryption scheme we use allows a certain number of punctures, a certain number of revocations before you have to throw out your key and start over. And so these like key rotations end up being expensive.
So you're just pulling it periodically to regenerate the key for failover purposes. Okay.
Yeah. So that's the downside. The positive thing is this can all happen offline, when your phone is on Wi-Fi or something. And I also suspect if we used kind of heavier crypto tools, we could probably reduce the amount of keying material that the phones need to download, which would be important in practice. I guess the other thing we did is tried to back of the envelope compute how much this would actually cost Google or Apple to deploy for, say, 1 billion users. So just as a baseline, the cost of storing the backed up data, so say if each user has 4 gigabytes of data, is on the order of $600 million per year. So yeah, this is 4 gigabytes per user per year, something like $600 million. And on top of that, the costs of the hardware that you need for SafetyPin to support 1 billion users recovering, say once a year per year, is if you use these really cheap hardware devices that we used is some tens of thousands of dollars. If you use industry grade HSMs, it's more like $15 million. So this is a lot, but relative to the cost of the storage, it's not clear that it's such a big deal. So, okay, so just to kind of end where we started, the goal of the system is to provide the same convenience of today's backup systems, but force the attacker to compromise many more HSMs before it gets any user's data. So I think more generally, I guess the reason why this project was interesting to me is that these encrypted backup systems are an example of where kind of cryptographic hardware can help us build much more trustworthy systems. Yeah, like we wouldn't have encrypted backup on our phones if we didn't have these HSMs. So I think that's a very positive thing. But at the same time, I am super skeptical of this kind of black box crypto hardware. It has implementation bugs. Who knows whether there's hardware backdoors in these systems? And as we've seen, it's not that hard with enough work and enough skill to extract the keys from these devices. So I think what I would like to see is more of these systems that make careful use of secure hardware, but at the same time are careful to protect against the compromise of the hardware itself. So I'd like to have kind of the benefits of secure hardware if it works, but then if it fails, we shouldn't end up with no security. We should kind of gracefully degrade to the state we're in today. So this is my hope for kind of future of secure hardware. And the paper and the code for this work are all online. And again, I want to acknowledge Emma Dotterman, who is the PhD student who is running this project. Yeah, that's it. Happy to take questions if people have any.
Could you maybe say something about parallelism? Because the way I understood the systems with the key on the HSMs being periodically deleted and the outsourced key re-encrypted, this sounds to me like it might be problematic if at Google scales, I don't know, 1,000 users want to access the backup at the same time.
Yep. Yeah, so I think one thing that saves us a little bit there is that, first of all, this is a very good question, is that the load is spread evenly across all the HSMs in the data center. So each HSM isn't going to see all of the load at once, right? Because, so there'll be, the load will at least be spread evenly. And then, I mean, it's not too bad for the HSM to serialize these requests and just do these decryptions one at a time. What it does is it's going to increase the user perceived latency of the backup. But even with this, so this 1 second number is actually computed with many concurrent requests to the hardware. So I don't think it's going to be that big of an issue.
There's one question in the chat. I don't know if you can see it. Or should I read it?
Yeah, absolutely. So this paper is mostly focused on physical attacks on the HSMs, and that's because if your HSM has a vulnerability that's exploitable over the network, or there's some of these ridiculous PKCS11 APIs that the HSM implemented incorrectly or implemented correctly, but the API, the spec itself is buggy. Yeah, there's no hope there. I guess to me, these attacks are always going to be around. Like if your phone is leaking your data kind of out the window, then it's not clear there's anything that we can do. But I think even if those attacks are not present, I think we still have to worry about physical attacks. So I guess I view these as kind of both important classes of attacks that are maybe at different layers of the stack.
So can I ask, just to understand the adversarial model, so you said there's lots of rekeying and so going on. So these devices can sample their own keys, right? So the data center is not trusted at all, everything, okay.
Yeah. So the devices sample their own keys, right?
So, okay.
There's still an issue, I should say, there's still an issue of making sure that the phone is getting the right public keys for the hardware devices. Right. So if the data center if you're getting the list of public keys from Google, you have to worry that Google is giving you real HSM public keys and not public keys for which Google knows all the secret keys. But that's, again, kind of a different layer of the stack. And there's kind of orthogonal work that looks at that issue.
In particular, if you say that, keys are blanked or deleted, this is, you don't assume that anyone honestly deletes things other than the hardware devices.
Exactly. Yeah.
Does a better PIN, like 8 digits instead of 4, increase the security of a safety PIN, or is it pointless?
Yeah. So, I mean, it does. So if you look in the paper, there's some expression for the attacker's advantage in some security game that we define. And essentially what we want to say is that if the PIN is, this is like also a simplified model, but if the PIN is sampled at random from some PIN space, then this is the advantage that you get is like something like the number of guesses divided by the size of the PIN space plus some other stuff that depends on the security parameter and other things. And so as the PIN space grows and grows and grows, the security gets better and better and better. Does this make sense?
Yep.
Yeah, concerning the rate limiting, isn't this or have there been a denial of service attacks on that, or how can you prevent this? I mean, it's not strictly related to you.
Yeah.
I mean, if I'm an attacker, I just try to lock out as many people as possible with low rate limits, like 10 per month. This should be easy.
Yeah, absolutely. So I think so I guess there's two questions. So one question is, if Google is trying to deny you service, then it's hopeless, right? Google can just delete your backup. They can turn off their data center. So the way it works today is that when you want to recover your backup, first you have to log into Google using your Google credentials. And then Google will let you talk to the HSM. So this is how they prevent a random person on the internet from, typing in 10 bogus pins and then deleting your backup, which is effectively what would happen otherwise.
Okay.
Yeah, that's a good point. So question in the chat. So have you considered using anonymous communication networks to break the link between the phone and the set of HSMs that are contacted? And if so, is the performance reason to avoid using them? So yeah, we thought about this a little bit, and mostly we're dissuaded because of kind of performance and complexity. And also, I guess, you know, in the kind of network that the HSMs are sitting in, it's not like the internet where the attacker might not see the entire network. It's the attacker's network. So the attacker really sees all the traffic between the HSMs. So it wasn't clear to us whether, you know, a Tor-like technique would buy you much in that setting where the attacker really can see everything. We thought a little bit about kind of private information retrieval techniques and this sort of stuff. But it just seemed like that was going to be much more expensive. But I think it would be interesting if there's something to do there. I think that would be pretty cool.
I have a question, if I may. Do you hear me?
Yeah, you're quiet, but I can hear you.
Okay. Well, my first question is on the threat model, on the quality of the threat model, namely, how likely is it, or does it make sense to think of an adversary who has the ability to compromise a Google HSM in order to obtain data of a user which is willing to share his data protected with a PIN on a server of a company he doesn't know? I mean, it sounds like to me, those people who make backups with PIN protection, those are the ones which are likely to click on any link I sent them in an email. So it's, you know, is it realistic to in the first place to consider this scenario?
Yeah, no, I think it's an interesting question. So just to make sure I understand your question is, if you're so naive as to back up your data with Google under a PIN, then you're probably naive enough to get compromised in all sorts of other ways, whether it's this social engineering or phishing or something like this, right? Yeah. So I guess for me, I think the goal is to defeat mass surveillance here, where what I don't like about the way these backup systems work today is you compromise one HSM and you get all the data in the data center, millions of users' data. If instead an attacker is forced to do some kind of social engineering, or launch an O-Day against a particular user, I feel like these attacks scale much more poorly, right? Because if you need to compromise 1 billion users, it's not. I mean, you could probably do it, but it'd be much louder and more detectable and probably more costly. So I guess, for me, these encrypted backups, the way they work, it's really a lot of data with very little protection, and it's a low-cost attack today. So I think this is about just raising the cost of the attack, not preventing anyone from getting your data, but just making it harder to do these kind of mass surveillance attacks.
Do you use online backups?
Do I?
Yeah.
I do. But I'm also I use a longish passphrase. But I actually worry more about, I worry as much about availability of my data as I worry about confidentiality. I think for me, these things are almost on par. Yeah. Do you? No. No, never. So where do you back up your data? I mean, this is also a question.
All up in my
I see.
No. Yeah, okay. And then my second question is a bit more outside of the box, maybe.
Yeah.
But I like to ask this because cryptographers want to skip this always. But what do we know about the quality of randomness generated by low power devices?
That's a fantastic question. So especially for these HSMs, which are really simple hardware devices, I think we know that in many cases, the quality of randomness is not very good. So there have been attacks. I think Nadia Henninger is maybe the main person who's looked at this, on Bitcoin wallets, hardware wallets, which are essentially the same type of hardware, same type of microprocessor. and found that there's a lot of nonce reuse in, say, ECDSA signatures that these things produce. And the reason for the nonce reuse is they're using bad randomness, and then you can recover the secret signing key and steal the people's Bitcoin. So I think there is evidence that for at least the lower cost HSMs, the randomness might not be that good. My guess is that for the things like the SafeNet HSMs, at least the simple problems are not there. They have some internal hardware random number generators, special hardware. Who knows how it works, but it's probably better than the really cheap devices. Does that answer your question? I'm not sure.
Yeah.
So, are there some more questions?
What does Google think about this proposal? Did you reach out for them?
Yeah, so actually Emma is speaking there next week, so I'm curious to see. My guess is it's a little bit too far out for them, but I'm actually, yeah, I'm curious to hear if
incentive to install this. I mean, there should be, if there comes more public pressure and people get more worried about their confidentiality, they will probably reach out for you. But as long as there's no public pressure, they will, I guess they will not care about increasing their complexity of maintenance.
Yeah. I guess to me, the thing that this, obviously I really enjoyed working on this project. I'm surprised at how good the performance can be. I think the thing I've realized in talking to people in industry is how kind of simplicity is almost even more important for them than performance in many cases. And since this it adds quite a few layers of complexity to what they're doing, I could imagine for that reason alone they would be skeptical. But I could imagine also them taking bits and pieces of this, so maybe not take the whole system, but take a couple of the ideas and use them to try to strengthen what they're doing at least.
Okay, thank you.
Yeah, thanks for the questions.
Let's see if there seems there are no more questions. Thanks a lot for the great talk. This has been nice feedback on the channel. So it was great.
Yeah.
Great having you. Thanks.
Yeah, thank you so much.